Hello, everybody. I'm gonna show you how to do the gizmos assignment 15.3, and we're gonna go to semester one. Let's see, 15, week 15 folder. 15.3 photoelectric effect activity, B and C. Here we go. This is a document. Okay. And you already answered these questions, so all you have to do is answer them again. It's okay to answer them again. You are going to get points for these questions, but I need you to answer them again, okay? So this is activity B, and I'm going to go on to clever.com, clever.com, and you log in as a student. I'm going to log in as a teacher because I'm a teacher. And here is my page. So I'm going to access my page, and then I'm going to click on the gizmos icon. And it's going to take me straight into gizmos, all right? So let's do the photoelectric effect. Click on that. And so here it is, all right? So now I'm going to put it on the side just because I want to look at my document as well, okay? I'm going to put this at 75%. Like that, okay? So it says set the wavelength to 300 nanometers and the photon flux at 10. So 300. So here we go, 300 nanometers. And then the photon flux at 10. There it is. Now turn on show voltage gradient. So there it is, show the voltage gradient. The electrons that are freed from the surface of the metal have a specific amount of kinetic energy. Faster electrons have greater energies than slower ones. The energy of emitted electrons is measured by setting up an electrical field that opposes their motion. The voltage of that field is the measure of its strength. So pretty much the voltage or the electrons are trying to overcome that voltage, okay? And so this is what we're trying to do, okay? The electrons are trying to overcome that voltage. Use the voltage gradient to measure an energy emitted of electrons. So I have potassium. Click on flash and observe the emitted electrons. Increase the voltage to 1.5 and click flash. Click the flashlight again. So I'm gonna do it at 0. So there it is. And as you can see, there's no voltage, so they go at normal speed. But now if I increase the voltage at 1.5, okay, if I increase the voltage at 1.5, pay attention because they start fast and then you're gonna see what happens, okay? All right, so let's try it again. And one more time. And so go ahead and write your observation in this box for number 1, okay? Now we need to measure. Let me see. Just because I wanna show you what I measured, not okay. How we measure that stuff. All right. So it says the energy of an emitted electron is measured in electron volts. All right. Electron volts, it's how it's the energy. That is the energy um, that an electron has. All right. An electron with an energy of 1 electron volt can overcome an electrical field of 1 volt. So this is an electrical field of 1.5. And so an electron with 1.5 electron volts can overcome it. So now here is the important part. In the gizmo, increase the voltage until you find the highest voltage that it still allows the electrons to reach the light bulb. All right. So I'm gonna try 1.5. So we said that at 1.5 it reaches, right? But I'm gonna see if maybe three, if maybe if I put it at 3 volts, maybe the electron can overcome that electric field, and they don't. The electrons do not overcome the electric field. So I'm gonna put it at 2.5. Let's see what happens. Nope, they're getting closer, but the electrons do not overcome the electric field. So how about 2.3? Nope, not 2.3. Okay, so let's see. 2.1. Let's do 2.1. Almost. So it's getting closer. All right, so it's getting closer. How about 1.9? Come on, 1.9. Nope, not 1.9 either. Okay, so it has to be 1.8. It has to be 1.8. And there it is, 1.8. Okay, so there it is, 1.8. So 1.8. That is how many electron volts it takes to overcome um, a the electron field. Okay. All right. So let's do, and this is the same answer for 1.8. Okay, for 300 nanometers. And now let's do calcium. Let's do calcium and see. Let's leave it at 1.8. Let's see if it has the same amount. And it doesn't. Okay, so let's go ahead and decrease it to 1.6. Okay, 1.6. No, that's not gonna do it. How about 1.4? Nope, not 1.4. Wow, okay. Let's do 1.2. Let's do 1.2. Okay, 1.2. Is 1.2 gonna overcome? Yes, it does. Okay, so let's try. Let's see if 1.3. If it doesn't overcome 1.3, then it's 1.2. Okay, there you go. It's 1.2, everybody. Okay, so 1.2. That is how many electron volts it takes to overcome the electric field. Let's do uranium, and let's leave it at 1.3. So not 1.3, and 1.3 is really tiny. So I'm gonna make a big jump here, and I'm gonna go to 0.7. 0.7. Nope, not zero point 0.7. Let's see, zero point 0.6. Let's do zero point 0.6. Let's do 0.6. It's getting closer. So it's going to be 0.5. Okay. So it's going to be 0.5. Okay. So let's do 0.5. 0.5. Come on, 0.5. And there it is. So it's 0.5. Okay. All right, so that is how you do this. That is how you fill up this table. You have to do the same idea with 250. So at 250 nanometers, all right, and leave it at 10, and just go back to potassium, go through calcium, and then go to uranium, and then change it again to 200 nanometers. Change the wavelength to 200 nanometers, and again go through potassium, calcium, and uranium. Okay. Analyze what patterns do you notice in your data, and again. Um, Please make sure that you write more than one sentence. These boxes are able to expand, everybody. So please make sure that you're writing more than one sentence, okay? Your explanations as well. Let's do activity C. So let's see, set the voltage to 0 volts and select potassium. So 0 volts and select potassium, okay? I will need a calculator and copy of a periodic table of the elements for this activity, okay? All right, so let me see. Periodic table of the elements. I have one. You can look one up. But actually, yeah, that's what I'll do. Periodic table. And then I go to images, and there they are. All right, so I have a periodic table available. Okay, and then a calculator. So I need a calculator as well. So here is my calculator. Calculator. And here we are. Okay, here is my calculator. Okay, so let's see. It is easier to remove electrons from some elements than others. The energy required to free an electron from the surface of a solid is the work function of that element, okay? So the energy required to free an electron from the surface of a solid is the work function. How much energy is required to liberate electrons from a material? In general, the difficulty of removing electrons increases from left to right across each of the rows from the periodic table. So here we go. So removing electrons increases from left to right. So it increases from left to right, so this way. So it is harder to take away an electron from lithium, I'm sorry, from boron than from lithium. Or it is harder to take away an electron from sulfur than it is from magnesium, okay? Look up potassium. So potassium is K, right here. Calcium is Ca, which is right here. And uranium is right here. Uranium is right here. Based on their positions in the periodic table, which of these elements do you expect to have the lowest work function? Which element will have the highest work function? So based on this, make which one is going to have more energy required to take away an electron, and which one is going to have less energy required to take away an electron, okay? So write your predictions, okay? Write for your predictions. Gather data. Use the gizmo to determine the highest wavelength for each element that still removes electrons. Fill in the first column below. All right, so let's do this. So let's see. So let's do for 550. Now let's start with 600. All right, let's start with 600. Nope, not 600. 500 nanometers. Okay, so 500 nanometers does the work. But now I have to see whether 550, no, now 550. Okay, how about 530? Ooh, 530. Okay. So 530, and they're really slow. So that is the highest wavelength of each element that still removes an electron. So 530. Did I do 540? I don't remember. No, I didn't do 540. So 530, everybody. So 530. So for potassium, it's 530. So 530 nanometers. Okay. Okay. So how about calcium? Let's see. How about calcium? So calcium. Um, let's see. Let's do calcium. Let's try it. Let's change it to calcium. Now 530. Maybe 500. Not 500 either. Maybe 400. 400. Oh, there you go. 400 does the trick, but now you have to figure out whether it's 400 or something else. All right. So I'm gonna let you decide that. I'm gonna let you work through that. Now, the frequency of a wave measured in hertz is the number of waves that passes a point each second. To calculate the frequency of an electromagnetic wave, divide the speed of light by the wavelength. All right. The speed of light is 299,792,458. Or approximately 3.0 times 10 to the 17 nanometers per second. Using the equation, calculate the frequency of each wavelength given in the table. Fill in the second column. So fill in the second column, everybody. So I have to, this is nanometers per second, everybody. This is nanometers per second. And so now what I have to do is I need to put the speed of light is c. All right, the speed of light is c. And the wavelength is 530 nanometers. So what I need to do is I need to grab my calculator and I need to put 3.0 times 10 to the 17. And please notice how I use this to write the upper script, the power, all right? And now I divide by 530, divided by 530. And I get, so I'm gonna write this number as 5.66 times 10. So whenever you see an E, whenever you see an E in your calculator, that is exponent, all right? So that is exponent. So 5.66 times 10 to the positive 14. So times 10 to the 14. Or I can do format, text, superscript, and you do a superscript by doing control period, all right? So you do control period. So that's what I'm gonna do. I'm gonna do 10, so control period, and that gives me to the 14, okay? And there it is. All right, so that's what I do for that. Let's see. Now, what I need to do is calculate. It says calculate the energy of a photon. The energy of a photon depends on its frequency. All right, the energy of a photon depends on its frequency. The energy of a photon in electron volts is equal to its frequency multiplied by Planck's constant. Planck was a German physicist, and he is credited with a lot in modern physics. Okay. In this calculation, H is equal to, this is Planck's constant. Okay, so 4.136 times 10 to the negative 15. electron volts second, electron volts second. Calculate the work function of each element in the table above, okay? So this is hertz, this is per second, and this is electron volts times second. So you are gonna have, when you multiply these two, this number and this number, you're gonna get electron volts, and that is what you're gonna have here. So let me put those numbers in. So 5.66. Oops. Let me do the parentheses. 5.66 times 10 to the 14. Whoops. Let me do that. Okay, times 10 to the 14 times Planck's constant times 4.136. 4.136 times 10 to the negative 15. Okay, so times 10 to the negative 15. Times 10 to the negative 15. There you go. Okay, so I multiply that and I get 2.34. So 2.34. That is the work function. That is how much energy these electrons have. Okay, and based on the calculated work function of each element, which element holds onto its electrons most tightly. Okay, so you can figure out whether it's potassium, calcium, or uranium based on the work function. Because again, the work function is the energy required to free an electron from the surface of a solid. Okay. Think and discuss. When the photoelectric effect was discovered, scientists were surprised that low-frequency light was unable to remove electrons, even when the light was very bright. In other words, scientists expected the low frequency to be offset by the light's brightness. Okay. So think about this, and this is why we're studying the photoelectric effect. This is about energy. Okay. So that is how you do this, everybody. All right. And okay, I think that should be good. All right. Have a good one, everybody. Take care.